Okay, so we'll continue with correlated equilibria. So let me remind you. So how do we define correlated equilibria? We had a random device, which was actually a probability space, so consisting of a set of outcomes, a probability measure on the set of outcomes, and a collection of information sets for each player. That denoted our random device. And together with this, we had, for each agent, a mapping from the set of actions, set of outcomes into the player's strategy set, which was a complete plan of action telling us what the ith player would do given the result of the outcome of the random device. Okay? So this was intuitively appealing. So we call this a correlated solution if it satisfied a certain condition. So actually with this, what we did was we expand. So initially we started with a standard game, pure strategies. We extended that to allow for agents to randomize. So in a way, we expanded their strategy set. With this expansion, for finite games, we were guaranteed the existence of Nash solutions. Now, actually, what we're doing is we're even further expanding this to a larger class. So what we would probably expect is to have more Nash, more solutions, okay? But the idea is when we expand the solution concept, we still have the idea of the Nash idea. No agent changes their plan of action given the plan of actions of the other agents, which was the same idea of the initial that we had for Nash solution when we first defined it. Okay. So this is intuitively appealing. Actually, there is a real-life application of this idea, which is, does anybody know? Which is the traffic lights. Okay. So in the last homework I gave you, one of the questions was about traffic crossing, two cars, well, not the last homework, the one before the last homework, two cars approaching an intersection. So they had the option of stopping and going. Okay. So you find the mixed strategy Nash solutions of that game. Okay. So traffic lights is a way to expand that game. So what do? We build traffic lights on the intersection. They go red and green. Well, they're not exactly random. You know, they stay red at a certain period of time, green at a certain period of time. But, you know, we arrive at those intersections at random times. Every morning when I come to school, I go through two traffic lights, and I never know whether when I arrive at that intersection, I never know it's going to be a red or a green. Okay? So actually, the traffic light is a very good example of using the correlated solution concept to induce a correlated Nash solution of a certain game. Okay? But the problem with this is, you know, mathematically it's very complicated, it's heavy-weighted. So last lecture we were talking about simplifying this. You know, given the random device together with the strategy, the plan of action based on the outcomes, we said this actually induces a probability distribution over the strategy profiles. Okay? So actually, we could take the outcome space to be the set of all strategy profiles. Okay? I'll talk about the probability measure in a minute. the information classes, well, here, they observe an outcome, and each agent chooses their own action. So, and they do that simultaneously. So we can take, when we're moving from here to here, it might be reasonable to take the information sets to be sets of the following form: Si, S minus I, in capital S. So set of all strategy profiles, okay? Set of all strategy profiles where Si, so how do I want to write this? Well, let me write it like this: Si, where Si is equal to Si prime. And what do we have? There exists an Si prime in Si. Okay. So it's the set of all strategy profiles where the ith component is fixed. It's like a strategy profile is chosen at random, and agent I only observes his component. Okay? Okay? So, okay, so far, so good. So far, ain't so good. So, let me go back to the Battle of Sexes game. Okay, so for example, in this game we had rain, clear skies. Okay, information set was sets of singletons, okay, and probability measures pi of R equal to pi of C equal to 1/2, okay. So rather than working with this, we take S to be the set of all strategy profiles. The information partition for player 1 to be SS. So that's going to be one set. Okay. So rather than choosing R or C, we choose one of the strategy profiles. Okay. Here, agents observe the whole thing. Here, what they observe is, they only observe, so when you look at this information partition, what they observe, the information they get is their own component of the strategy profile chosen. Okay. And for player 2, again, there's two partitions. So player 2, when I look at this, I understand that player 2 only observes the second component of this. Okay? So far? So good? What about, so I have to define a probability measure for this case. Okay, so what I'm doing is I'm translating this animal, where the outcome space could be something arbitrary, probability measure could be something arbitrary, information set could be something arbitrary, into probability measure, a random device where the outcome space is fixed by S, and then we fix the information partition as given here. Okay. So let me call this prime. Okay. So we need now a probability measure, pi prime. And how would you define that? So let's take a look. Let me use this side. So pi prime of SS should be equal to what? So I want to translate this into this new world. Pi prime of SS should be equal to what? Yep. Sorry? Pi prime of O. Why? They both get? Okay, but you see this is a probability measure. It doesn't have anything to do with utility. Player 1 playing S is? But you see, you have a feeling. You're talking. So when we go back here, you're asking the natural question. You're asking, with what probability would the players play S? S. That's what you're thinking about, which is the right thing to think about. Okay? But then, in order to give that, what do we need? Well, we do have probabilities here. But the probability is the probability of rain, the probability of a clear sky. You need the correlated strategies, right? Correlated strategies tells us what actions they will take based on the outcome of the random experiment. So in order to define this, what I need is the correlated strategy of a player. So let's take a correlated strategy. So let sigma 1 be such that sigma 1 of R is equal to, I don't know, the one we picked last lecture was O. If it's raining, player 1 will go to the opera. And actually, let's pick it sigma 2 of R to be the same. And sigma 1 of clear sky, they'll go to the soccer match. Okay. Now let's write pi 1 prime of SS. The probability of? Uh-huh.
So with probability 1/2, a player here, when it's clear sky, he will go to the football, to soccer match.
Uh-huh. Well, so let's go step by step. This is, first of all, we should be defining it in terms of pi, right? Pi takes outcomes. So maybe we should write, it's the set of all outcomes omega in capital omega such that sigma 1 of omega is equal to S and sigma 2 of omega is equal to S, right? So what does this set consist of? Sorry? It's, right? the outcome that is mapped to S by omega 1 and S by omega 2 is C. So that's equal to 1 over 2. Okay, so far so good? So what is pi 1 prime of SO? You all see that? So the set of outcomes which are mapped to S by sigma 1 and O2 by sigma 2. But there is no such outcome. Okay? Each outcome is mapped always to the same. With this correlated strategy, each outcome is mapped to the same strategy. So that's pi of empty set, which is equal to 0. Okay? So far, so good? And then we can continue. Okay? So we have pi prime. Now, so that completes the random device, okay, the probability space. Now I have to find a representation of this, which would be well, the way we constructed these probability measures, it looks like, so let me use sigma I hat, okay? So sigma I hat is a function from the set of outcomes. So it takes a strategy profile, and it should assign a strategy to it, okay? And the natural way to take it is to take it to be SI, because each agent only observes their own component. That's the only information that they have given here. So that's what we have. Okay. Yep.
Why do we define their probabilities in terms of the agents? I mean,
In terms of what?
In terms of the agents. Why is it pi 1 SS? Is there a pi 2 SS?
Oh, no, I'm sorry, there's no one here. That was there's no one there. That's pi prime. There's only one probability. Okay? Okay? Yeah, thank you. Okay? So that's how I would translate it. But of course, player can use a different strategy too. So the nice thing about this structure is, so given any correlated strategy solution, okay, I can translate it into a form where the outcome, set of outcomes is S, strategy profiles, and the information sets are just as we defined here. Okay? The nice thing about this structure is that in all these, once the game is fixed, this will be fixed, pi prime will be fixed, information sets will be fixed. So then I wouldn't have to worry about this part. Okay? But agents could use different strategies. Okay? And that's what we were doing last lecture. We were dropping all this part and just concentrating on that part. Okay? And the nice thing about this is, first, mathematically it becomes more simpler. Okay? And actually, we fixed this too. Okay? So the only thing that I would have to worry about is the probability measures. Okay? And that's what we were doing last lecture, and where that's the part that you got confused with, the Bayesian updating part. Okay? So let me go back to that world. Let me go back to that world. Let's go back with the battle of sexes. That was the example we were working with. One, two, okay. So we said, so we fixed the set of outcomes to strategy profiles. We're going to define probability measures on the set of outcomes. What was the example that we had last lecture? I think we picked 1/3, 1/3, and then this was 0. This was 1/3. So that's what we had. The information partition is, again, everybody observes their own signal. Okay. So what they had was follow the instruction, follow the recommendation. Okay. So think about a strategy profile is chosen at random. Every agent is recommended to play their own component. So agents have two options: follow the recommendation, play something else. Okay? So they will follow the recommendation if their expected utility by following the recommendation is greater than the expected utility by playing something else. Okay? That's what we were doing last lecture. So let's let's take player one's perspective. So player one could be recommended to play S. So the random device selects an outcome. Okay. If player one, not a strategy profile, if player one is recommended to play S, it means that the outcome of the random device was SS or SO. Okay. So player one is informed. You're player one. I tell you that you are recommended to play S. What is your expected payoff? Well, so so here maybe it might be a good idea to think about in terms of beliefs. Okay, so you're told to play S. What do you think the other players told? Either S or O, right? Both of them are possibilities. So if he's told to play S and if he follows the recommendation, your payoff is going to be 2. But he could be told to play O and he follows the recommendation, then your payoff is going to be 0. Okay? We assume that player 2 will follow the recommendation. Okay? And we're considering whether we should deviate from the recommendation. So with what probability would I believe that player 2 is told to play S? And 1/2, right? Actually, it's 1/3 divided by 1/3 plus 1/3, right? Initially, I was believing that this outcome will be realized with probability 1/2. This outcome will be realized with probability 1/3. This outcome 1/3. This one 0. Once I'm giving this information, I know that the result of the random experiment is one of these outcomes. Okay? So using Bayesian updating, that's what we get. Okay? With what probability would I believe that is told to play O? 1/2. Again, the same calculations. 1/3 divided by 1/3 plus 1/3. Okay? So, his expected payoff, if player 1 plays S, that will be his expected payoff. Okay? But he could say, well, I will not follow this recommendation. I will do something else. What else can he do? Play O. If he plays O, what is his expected payoff? It's 1 or 1/2. Okay. So that's where actually we got confused last lecture, right? That's where most of you got confused. So let's think again. Okay. I'm told to play S. Okay. So once I'm told to play S, what do I know about the outcome of the random experiment? Once I'm told to play S, what do I know about the outcome of the random experiment? Random device. Sorry? SS or SO, right? It's one of these, okay? So I still believe that player one is told to play S with probability. Given that I'm told to play S, I believe that player two is told to play S with probability, with likelihood, 1 over 2, and to play O with probability 1 over 2. Okay? So if I believe that he's told to play S with probability 1 over 2, that is 1 over 3 divided by 1 over 3 plus 1 over 3, and if I play O, how much do I expect to gain? 0, right? So it's 1 over 2 times 0 plus 1 over 2 times 1, which is 1 over 2. So far, so good? Okay. Yep. Okay. Okay. So I'm told that S1 should be, I should use that as, let's see, to play S, okay? So what are the possible outcomes of the experiment? It's either SS or SO, right? Okay? So how do I find my expected payoff? It's U1 of whatever I play, let's call S1 prime, okay? And my opponent follows the recommendation S2 times, okay, the probability that this outcome is realized, okay? But then, you see, I already know my part, okay? So the only thing I ask is, what is the probability? So this could be, let me write S, or it could be O, okay? So I already know my component. So the only thing random here is that I don't know is what player two is told. And we assume that player two will play what he is told to play, what is recommended to play, okay? So given that I'm told to play S, I know that the outcome is one of these. What is the probability that actually the outcome is this? Okay. Well, if each outcome is equally likely, and that's, well, in this set, those two outcomes are equally likely, or if you like, you know, use Bayesian updating. So you're actually looking at probability of SS, okay? Well, we're looking at probability that player two is told S. When is he told S? Okay. He's told S when the outcome is either this or this. Okay. So probability that S2 is equal to small s. But under what condition, given that player one is told S? Okay. So you're doing a conditional expectation calculation, conditional probability calculation, okay? So what is that equal to? That's probability that these two events occur jointly, which is probability of SS divided by probability that S1 is equal to S. And what is that? Probability of SS is 1 over 3. Probability that S1 is equal to S is probability of SO, SS. In those two cases, the first component is equal to S, which is equal to 1 over 3 divided by the probability of this is probability of 1 over 3, probability of 1 over 3, okay? So, okay. So the key thing is, okay, when I calculate the probabilities, I use what I'm told. I'm told to play S, okay? So by that, I conclude that automatically the outcome is one of these. So the probabilities are fixed. But I might play S, in which case, these would be you see the payout, the probabilities are the same, okay? But I can change my mind. I can change S1 prime. I can play S, in which case my expected payoff is going to be this. I can play O, but when I play O, nothing changes about the information that I'm given. I'm already told to play S. So I already know that the outcome is one of these, okay? So when I think about playing O, the probabilities doesn't change. The only thing that changes is my Bernoulli payoffs because the outcome changes, okay? So far, so good? Yes, sir.
Why isn't updating? We might deviate when we play O, for example. Why don't we do P of S2 equals S, given that S1 we play O?
Given that S1, well, but you see, there's two things. The probabilities are based on the outcome of the random experiment, okay? Probabilities depend on the random device, okay? But this is, when we're doing, that's a decision that I make, okay? So I'm going to toss a coin. It's going to come up either heads or tails, okay? So, and if it's heads, I'm going to, so let's think, rather than heads, tails, on one side there's an S, on the other side there's an O, okay? So I flip it and I say you should play S, okay? Well, if rather than saying, well, rather than playing S, I'm going to play O. When you make that decision, does the result of the random experiment change? No, okay? That's why these probabilities don't change, okay? First, the random experiment is done, and the result of the experiment is independent of our actions. Okay? Yes?
If deviating was better off, then the first player would deviate, and the second player should know that the first player is going to deviate. And so if that's the case, this should be a more complicated.
Well, the thing is, of course, the same idea. That was the idea that one of your friends also had last year. So the same idea applies to normal Nash solution concept. So when we talk about deviation, when we define Nash solution, okay, we said no agent should have an incentive to deviate. But still, so when I deviate, take regular game, Kurno Monopoly agent, not Kurno, not Monopoly, Kurno Duopoly, firm one decides to deviate. And when we talked about that deviation, we didn't think about firm two also deviating, and because of that. So yes, there's a more complicated solution concept, equilibrium notion, which considers deviations which are actually credible, okay? So when I deviate, you can also deviate. And because of your deviation, actually, at the end of my deviation, I might not gain. So that's not a reasonable deviation. But in the Nash solution concept, that's not what we look at. We just assume if my opponents stick to their strategies, do I gain by deviating? Okay? But yes, that idea is a good idea. Unfortunately, other economists have already considered, other game theorists have already considered, and there is a solution concept. I'm not sure whether we'll have, probably will, given that there's only a few weeks left, we will not be able to get into those things. But there are, you see, both nice and bad thing about game theory is there are many solution concepts. So there are, actually, that's one thing that, it has been criticized for some time. If you're going to use game theory to predict or prescribe what players should do, well, there's many solution concepts. Which one should you use? Okay. So on one side, that's something bad. So there's the Nash solution, and there are problems with the Nash solution, just like the one that you mentioned. So what game theorist has done? Invented new solution concept, new methods to make predictions and prescriptions. So you have to be careful when you're using them. Some of them are valid in some problems, some circumstances. Some of them are not, okay? But in the Nash solution concept, we're looking at Nash idea here. we assume that the other players stick to their strategies, and we ask, does each individual, assuming that his opponents stick to their strategy, gain by deviating? Okay? If the answer is no, we have a Nash solution. Okay? That's the Nash solution under this notion we call a correlated equilibrium. But it's actually nothing but a Nash solution of a more expanded game. Okay? Okay. So here, when we look at this, when player 1 is recommended to play S, he doesn't have an incentive to deviate, given that his opponent doesn't deviate from the recommendation that is given. And then we check for O. So player 1, so as a result of the random experiment, player 1 could be recommended to play O. Then he can follow the recommendation. If he does, what is his expected payoff? 1, right? So if I'm player 1, if I'm told to play O, I know it means that the outcome is one of these, but the probability of this outcome is 0. So I know for sure that my opponent is told to play O. And again, we assume that that player will follow the recommendation. In that case, my expected payoff would be 1. If I deviate from that recommendation, what is my expected payoff? It's 0, exactly. Again, given that information, I believe that my opponent is told to play O. And we assume that the opponent will stick to his strategy. So given my belief that he's told to play O, if I deviate from O and play S, my expected payoff would be 0. Okay? So far, so good? So far, so good? So this probability distribution, we will say, so we do the same exercise for player 2, but the game is, symmetric. You can easily, it will yield the same calculation. As a result, we would conclude that the probability, so the way we will state this is pi is a correlated of gamma. Okay. Okay. So far? So good? So rather than saying, rather than constructing a random device with some arbitrary outcome space, some partition, all that stuff, we fix the random device to choose a strategy profile. Okay? And then as the player's strategies changes, the probability measure changes. Okay? Okay. So as a result, I can identify, this is fixed, the structure of this is fixed. Here, it's follow the recommendation, play something else. Kind of fixed. So the only thing that matters here is this. So we identified this 4 tuple with a single element. Okay? So actually, when I say pi is a correlated solution of gamma, I mean the 4 tuple constructed in this manner is a correlated solution in the initial sense that we defined of the game gamma. Okay? Okay. The nice thing about this definition, well, the bad thing about this definition is it's not as intuitive as this one. There's the traffic lights. Okay, and there could be, look, the example here, look at the weather condition. If it's rainy, go to opera. If it's clear, go to soccer. Okay? They don't flip a coin. Okay? They don't choose a strategy profile at random. They look at something that they can observe. So this is more intuitive, but it's more complicated. Moreover, this is simpler, but it also has a nice mathematical structure. So what is pi? Pi is the probability distribution over strategy profiles. Okay? Well, given the set is finite, we can identify pi. We can identify pi, in this case, as a 4 tuple. There's 4 cells, so 4 numbers would identify pi. So I can think of this as an element in R cardinality of S. Okay? But then once I do it, I can use the algebraic and topological properties of Rn. Okay? So I can add probability measures. I can take convex combinations of them. I can talk about sequence of probability measures. Okay? But when your outcome space is arbitrary, if it's rain, clear, how are you going to talk about distance and all that stuff? How are you going to do addition, whatever? Okay? Here, it's very nice. Okay? So far, so good. So from now on, when I talk about a correlated equilibrium or a correlated strategy solution of a game gamma, what I mean is a probability distribution over S. Okay? A probability measure over S. Any questions? Any questions? So let's formalize what we did here, which was actually what we're doing 3 lectures ago. So what do we have? Well, some strategy profile S is selected with some probability. Okay, so some strategy profile S is selected. Once that S is selected, agent I is informed about the ith component. Okay, so what can he do? He can follow the recommendation. Okay, or deviate from it. Okay. So, but in order to find this payoff, I need what the other agents would do. So what do I do? Well, the other agents might play some strategy profile, S minus I. We assume that they stick to it. Okay. The problem is, player I only knows his component, does not know what the other agents would do. But what does he know? What does he have about the other agent's actions? He has a belief about what they would do, right? He has a belief about what the other agents would do. So what is that represented? How is that belief represented here? So we're talking about the probability that the other agents are told to play S minus I. Given that he's told to play Si, I'll simply write it like this. So what do we use to find that probability? We use pi. Okay. So given that I'm told to play Si, what is the probability that the other agents are going to play told to play S minus I? And we assume that they will play what they're told to play. And that is independent of the action that I take. Okay? And what do we do? Of course, we don't know what S minus I is, so what do? We take the summation. Okay. So that's the expected payoff that I would receive if I follow the recommendation, if I play Si. Okay. That's the expected payoff I would get if I deviate to something else. Yep.
Is it SI prime or SI?
This is SI, this is prime. There wasn't. That's SI prime, that's SI. Okay? So what do we want? We want this number to be greater than or equal to this. Okay? And what do we want this to be the case? We want this to be the case for any recommendation that player I receives. Sorry? And for every player, exactly. Okay, so far so good? So far so good? Any questions? Okay, so far it ain't so good. There's one problem there, which is? Sorry? How do we define SI prime? So very good. You see, the accounting checking, you should check if everything is accounted for. S minus I is accounted for. SI is accounted for. I is accounted for. Pi is given. We're going to write that. Okay. So that's not prime, I. SI prime is not accounted for. So what do we also need? For any SI prime in SI. For every possible deviation, his expected payoff should be not more than the expected payoff he gets by following the recommendation. So far, so good? So far, so good? Well, so far, still, it ain't so good. There's still one problem, which is? Well, we're talking about a conditional probability here. What if? What if? What is 0?
Player I is never recommended to play SI.
Exactly. You see, what if, for example, if this was also 0, now 1 over 2, 0, 0. Player 1 would be never recommended to play O. So it's not meaningful to ask what the conditional probabilities are going to be when player 1 is told to play O. Okay? So what do we need to do? We need to say that you should check only this condition if an outcome in which player I is told to play SI is selected with a positive probability. Okay, so we need to add that condition too. There's several ways to, yep.
Summation of an outcome where SI is played.
Mm-hmm.
S minus I is greater than 0 for every
Okay, summation over
S minus I.
S minus I. So this means that there is at least one outcome in which player 1 is told to play SI. Okay? So if this is the case, then the expected payoff that player I would get by following the recommendation should be no less than the expected payoff that he would get from any deviation. Okay? So far, so good? So if this is the case, I wrote it in a little opposite direction, but if this is the case, then pi is said to be a correlated strategy solution of gamma, or correlated equilibrium of the game gamma. Again, when you look at it, it has the same flavor of the Nash solution. Okay? Nobody gains by deviating. Okay? So far, so good? So far, so good? Our time is almost up, but let me do one more thing. So when this animal is positive, if I multiply both sides by this, nothing will change, right? Multiplying both sides of an inequality with a positive number will not change anything. If it's equal to 0, when I multiply both sides by 0, what happens? They're equal. Automatically equality holds. Okay? So But if I multiply this animal with this, what do I get? You would get pi of S pi minus S. Okay, so I can remove this condition. Remember the definition for conditional probability? Divided by the probability of Si, which is summation P of Si S minus I over S minus I. So multiply both sides by the same animal. This cancels out. Okay? So this is an easier formula. You don't have to calculate conditional probabilities. You don't have to check whether Si will be recommended with a positive probability. So this is equivalent to what we just had. It's, you can use this formula. It's easier to use. No need for calculating conditional probabilities. No need for checking positivity. But it's less intuitive. The other one is more intuitive. I say, I'm told this. What is the likelihood that my opponents are told that? So the initial formula is more intuitive, a little bit more cumbersome. This formula is simpler, less intuitive. You can use either one. Okay? So far, so good? Any questions? That's it for today. Have fun.